G'day. My name's Nathan. I'm a machine learning engineer at Atlassian. We make Confluence, Jira, Bitbucket, Trello, hopefully some of your favorite products. Today, I'm going to talk to you guys about our journey with machine learning in the generative AI space, fine-tuning LLMs, but sort of end-to-end spectrum. So from considering your problem through to dataset generation, fine-tuning your model, and evaluation. Mostly I'm going to talk through general rules and frameworks we use internally, as well as a couple specific case studies on dataset generation and evaluation. And then I'm going to pass off to my colleague Brian, who's going to go through a more specific and concrete example of how to fine-tune and how to fine-tune at scale using Databricks. So, fine-tuning LLMs and using LLMs in general is a complicated space and has mostly hit all of us in the last year or so. And it largely invokes new questions that we haven't had to ask before around largely if it's worth it, because it takes a lot of effort. The models are very expensive to serve, but it's also very easy to apply it to problems. So I'm going to talk through the general developer flow as well to talk about a platform that's useful for your practitioners to actually develop and evaluate LLMs on, as well as what that journey looks like for your practitioners. So what are these sorts of problems you're going to ask yourself when you're considering fine-tuning LLMs or using them in general in products? Firstly, it's how do we justify the amount of effort that goes into fine-tuning an LLM? Because it's not just pressing a button, spending some money on your cloud compute, and then ending up with a model artifact. You're going to fine-tune plenty of models, you're going to iterate on your data set plenty of times, and you're going to have to spend a lot of time constructing that data set and then tweaking it. And then you've got to work out how to evaluate it. Because unlike more traditional ML problems, you're probably not going to be content with just looking at your cross-entropy loss and seeing your eval loss go down and know, yes, I've got confidence my model works. Finally, I'll talk a little bit about serving expensive models at scale and just general rules that we have internally to make sure that practitioners are developing models that can be served reasonably inside our serving infrastructure. So, LLM fine-tuning is super uncertain. You might actually put a lot of time into your data set and model and have confidence that your method is good and it doesn't work. So how do we decide if we're going to fine-tune? My general advice is that fine-tuning LLMs should be your last resort. And I promise not every slide is going to be discouraging you. But the general questions that I'm going to ask myself when I agree that yes, my problem needs an LLM are firstly, do I have an evaluation data set? This is a predicate for the rest of this. So I'm going to assume that you have at least 200 good examples and a way to evaluate if your system is actually working well. And the second thing is you've decided, yes, this is a problem that a large language model can help me solve, either as part of the pipeline or as the entire pipeline. First step, you should ask yourself, have I tried using an open source model or a proprietary model with zero fine-tuning, with zero shot or a fixed few shot prompt, where you've given it some examples that are similar to the problem it's going to solve, and have you evaluated there? And then you ask yourself two questions. Firstly, am I doing well enough in terms of output quality? Am I actually solving the problem? And the second question is, how is latency? Is this a good user experience? Because you might find that you're actually good with zero shot and you're getting fantastic outputs with a 70 billion parameter model, but latency is way too high. And this might even be an invisible step in your pipeline, and it causes a really bad user experience. So if you have either of those problems, I suggest moving to RAG, Retrieval Augmented Generation. This is still moderately high effort, but nowhere near the same amount as fine-tuning. So for anyone who doesn't know, this essentially means creating a database of information relative to your problem, and then finding a way to inject relevant information into your prompt. So you've still got a few shot prompt, but the information is relative to the prompt, to the query from the user. RAG works really, really well, and you can use much smaller models with much lower latency because your model's not relying on knowledge, it's instead relying on general reasoning from information that it's already got inside your prompt to solve the query. If either of these work well, you're happy Homer Simpson. You probably don't need to move to fine-tuning, you can save yourself all the effort. But if you've gone through these steps and you still can't solve your problem with LLMs and you're determined, we move to fine-tuning. So, guidelines. So when you're fine-tuning a model, most of you know you need a base model or foundation model. How do you decide on that? A large theme in what I'm going to tell you is going to be prioritizing pragmatism. So very quickly, on the code you use, I suggest using pre-existing trainers and frameworks. And once you know that your code works, your models are training, your training is distributing across all your hardware, I usually fix it. I say I'm not gonna spend a bunch of effort spending hours and days of time trying to get another 10% GPU utilization, because that time is probably better spent making your data set higher quality and getting a greater coverage of your problem. Secondly is prioritize small models, because if you find a smaller model as you move up in size that solves your problem, you don't really need to go any larger. You don't need to worry about latency as much, and your problem's gonna be easier. Your training time's also gonna be lower and cheaper. Next is prefer adapters like LoRa over full parameter training. I assume most people will know what LoRa adapters are, but for anyone who doesn't, LoRa adapters, essentially this method allows you to take your pre-trained foundation model, fix it fully in place, and then use a smaller set of trainable parameters. So your model could be in the 7 to 14 billion parameter range, but you train only 10 to 100 million parameters. Again, this lets you train really, really quickly. They learn very quickly. You can also vary the complexity and the size of these adapters, but probably the most important point here is that if you're using adapters and you're training adapters on the same base model, you can serve them on the same hardware. This largely solves your cost of serving problem. You can serve tens to hundreds of adapters for the same base model on shared hardware. This also means you've got a big enabler for building features based on LLMs, even if they're very high value features for your product, but you expect very low throughput, that's fine. LoRa's are tiny, they're in the tens to hundreds of megabytes, not in the tens of gigabytes range, and they use very little memory. So your memory footprint's gonna be much lower. So I follow this general spectrum, top row, then bottom row, when I'm considering a problem. I always start with LoRa adapters on the smaller range from like 3 billion parameters onto 70-ish. And then if that's not working, then I move to full parameter training. Again, because full parameter takes a lot more time. And if you can stay inside that top row, you're gonna be much happier when it comes to serving. Another thing is, and you'll notice these dotted red lines in each of these spectrums, your threshold for the size of models should be much higher for LoRa's. The reason for that is that if you can share 10, 50, 100 use cases on one set of compute, one instance in your cloud, then you can serve that 70 billion parameter model and you can train on top of that knowing I'm not gonna need a separate instance for every use case because I'm pooling those resources. If you've got a full parameter trained model, it needs its own resource. That's the reality. So then you're incurring like a fixed cost for every use case rather than sharing them. I talked a little bit about frameworks before, just quickly. If you're on single GPU, Unsloth is really good. They've got super optimized kernels. You'll train with low memory and very fast training compared to not using it. Beyond that, if you're going to multi-GPU, you can still use trainers. So the transformers trainers or the TRL trainers based on your task are really good. You're probably moving, when you're going to multi-GPU, beyond normal data parallels. So that's where DeepSpeed and FSDP come in on the Torch side. These are still relatively easy to use, and it's very easy to trigger on single node with multiple GPUs. If you're going to multi-GPU, things get a little bit more complex with regards to your distribution. You're probably in HPC setup with something like Slurm or Kubernetes, or you're in a Spark setup and you can use something like the Torch distributor. And Brian's actually going to talk through how to do that later, so you can talk about how to train models at scale, multi-node, multi-GPU using Spark. Finally, you actually get to fine-tuning. So you know which models you want to consider, you're gonna move along that spectrum. How do you decide which one to agree on? That is very dependent on your evaluation data set. But as a sort of necessary condition that I advise internally when people are trying to set a lower bound on the size of the models, I basically tell them throw your whole training data set at it, don't use any regularization, and just see if it can overfit. If your model can overfit to the problem, you at least know that you've got a sufficient number of trainable parameters and sufficient complexity that your model can memorize the problem. This doesn't mean it's going to generalize well, but at least it gives you a lower bound on the size of either your adapters or your full parameter model. Super useful as well when you're trying to work out the rank of any adapters is that you can just keep increasing R and changing those hyperparameters with the same model size if you want to stick with 7 billion, for example. Beyond getting that lower bound, you're going to have to evaluate on your own problem. So let's get on to how we actually evaluate. So this is a quick slide for something that we do internally. And it's a kind of useful framework we've got for when we already have an LLM-driven product inside the product. So this is already deployed. For context, we always deploy our AI-driven features internally to Atlassian customers inside our own instances first. And the reason we do that is we don't care quite as much about if an employee has a bad experience with the product, and it's a good way to get internal feedback before we push to customers and potentially make their experience worse. So the first thing we do is we dog food our feature to internal customers. And then separately, whenever there's an LLM-driven event, which has a customer query and it's got a prompt and it has an output, we store that in a database. On top of that, we have a bunch of LLMs in the background, often just variants, open source, proprietary LLMs that are given the same problem and then create variants of that output. We save that in a separate database, and then we pass those variants to LLM judges for scoring and voting. And then we save those scores. And what that lets us do is create a more rich data set that's actually built on top of user queries, so we understand the distribution of the sorts of questions that people are asking. And we can improve the quality of the next round of fine-tuning. Or we can try different prompts. So it lets us vary things in internal production and improve the quality of our outputs. Because we've got multiple variants and we've got scores as well, this is a great way to also create preference data sets for anyone who wants to do something like DPO or RLHF if you actually do want to use these scalar scores. But what if you can't do that? What if you do have your own problem that you can't build this sort of POC and deploy internally? You need to actually fine-tune a model from step one. Then you resort generally to the standard ML structure for your problem. You're going to create your training data. You're going to train your model or multiple models. You're going to evaluate them offline on the data set you've created. If you're not doing well offline, you sort of start again and you start enriching your data set. You find the areas where you're not doing quite as well, and then you keep going until you're happy offline. Then we deploy internally. We see how we're doing on realistic problems, and we might iterate again. This is super useful, and now I'm going to go into the actual case study. So the case study is going to talk about how we generated training data for a code generation use case internally. I will not be more specific about what exactly it was, but you may be able to guess. And then I'm going to, after going through that framework, talk about how you could translate it to a completely separate task. And then we'll move into evaluation and how we evaluate how the model is doing. The good news is this framework works for both offline and online evaluation. So by online, I do mean when you're using it with customers. So we've got code generation. This is our use case, and we needed to generate a data set. So we had a very talented engineer internally who came up with this framework, I think over a year ago, which is now sort of translated into the common area of, you might call it RAG-generated data sets. In short, his solution to this can be broken into a few steps. It's using LLMs at all of these steps except for the first one. So firstly, we create a corpus of information. So for our programming language that we need to generate, and the examples I've given are sort of basic, as if you've got a math library with power and multiplication and addition. We pass that into something like JSON, so we've got a structured format that we can then use to inject into prompts to then generate examples. So once we've got a nice structured format rather than ugly HTML, we can go into the 4 steps. And the 4 steps of generating the data set are generation, paraphrasing, complication, and cleaning. And what I mean by that is that for inside our programming language, every operator, every function, every class, we have a JSON, which has a description of it, the input signature, the output signature, and some examples, and its name, obviously. We create at least one example for each of these, and we do that by passing it to the LLM and saying, we have the following function. I want an example of a natural language query that a user might ask that elicits the use of this function, and then we get the output. So a user might ask, what's the sum of 5 and 8? And the output is sum, open parentheses, 5, 8. Super easy. This gives us good coverage over the base functionality of our language. Secondly, users often have a variety in the way they ask questions. So they might use punctuation, not use punctuation, use colloquialism. So the next stage is to paraphrase, to take the same inputs, change the user's inputs, and optionally, you can also change the exact values that might get passed in. Instead of 5 and 8, you might say 105 and 620. This gives us a little bit more variety in the questions that are asked, and it multiplies the size of our data set. Complication, for us, then meant iteratively picking pairs of valid types, ones that would interact nicely with each other. So the outputs from one function are a valid input to the next function based on the signature, and combining them. So this gives us an iterative way to create examples that are as complicated as you want. And finally, because we've used the LLM 3 times to generate examples, it might not be perfect. So what do we use again? We use the LLM to then go through each example and to ask, does this make sense? Does this seem to answer the user's query? And is the user's query ambiguous? Because if the user's query can be interpreted in multiple ways, it's more difficult for the model to learn. And realistically, we might not want it to learn one interpretation of it. So again, generation, paraphrasing, complication, and cleansing. This is great for code generation, but how could you apply this somewhere else? So another example we've got internally where we're using this exact framework is pretending that you want to do something like build a model that specializes in one sort of question answering. So an example might be, I want to, and we're not doing this as Atlassian, you can guess, but you might want to build a QA bot for medical cases. So what do? You've got your data set at the start, and instead of having data set that is from programming languages documentation, you just might have medical textbooks. And you might have paragraphs on tuberculosis or bronchitis. And you might generate something where the question is persistent coughing a symptom of bronchitis? And then the model can respond. And that's your initial generation. And your paraphrasing might change, is it a symptom, to is it the most commonly presented symptom? And then the next one might be, instead of just having a single paragraph, a question and an answer, it would be combining multiple paragraphs, because that's how it's going to work in your RAG system. You might have a paragraph on bronchitis, a paragraph on different types of infections. You might also remove the actual answer from your prompt, and then the model might have to learn to say, I'm sorry, I can't answer this given the given context, which is going to be very common in your RAG-based tasks. And then finally, you cleanse it. And your cleaning should, in this case, be saying, does it answer the user's question using only the information found in the prompt? You can tweak these steps a little bit, but I found that it provides a very good high-level framework that you can translate to almost any task of fine-tuning if you don't have an evaluation or training data set ahead of time and you want to generate it. Now you've got your training data and your eval data, you can get to actually training your models. How do you evaluate if it's doing well beyond something like accuracy? Because often if you've got 10 to 20,000 training examples, and you might have a few thousand evaluation examples at least, it's not super easy to identify where you're doing poorly, especially if it's not easy to categorize your examples. So what we suggest, and what I do internally, is to cluster. And we cluster both the text in the input from the query side, not the entire thing, and the output from the model. And this gives us themes. The clusters for your input text are often what sort of queries are users putting in that often get wrong. What we found is that we had clusters around, for example, Spanish language, because we have Spanish developers. Our model did not support multilingual, and it helped us identify which clusters we could actually tackle. Output theme clusters were often themes where the model is consistently hallucinating. So in our code generation example, we found that commonly we were using, the model was outputting functions which did not exist, but did exist in a very, very similar language that must have been a part of the pre-training set. So based on this analysis on the inputs and outputs, we can start to identify points on where's the model doing well, where's it doing poorly, and which areas where it's doing poorly can we address this in the data set. So if you find themes where the model's doing incorrectly using a function that does exist, or it's doing badly at a user query that it could and should be able to actually answer, you can start adding more examples to your data set based on this. So it gives you a guided way to start improving your data. Unfortunately, the first data set you make is not going to be the last one, and you're going to spend way more time cleaning and adding to your data set than you're going to spend actually training models in terms of developer time. But that's just the reality. The other thing that you can do is if you find that your system itself, the actual product, is getting a lot of queries that it simply can't solve, in production, parallel to your LLM call, you can have a separate call to something like a classifier that you've trained to, for example, ask, is this an English query? Does it use any of the following functions, or would it elicit any of these functions that we know doesn't exist? So you can start building a classifier that basically says, can the LLM actually solve this? And if not, you ignore the LLM call and you can return something to the user with a bit of information on why you don't expect that their query can be solved. So this is not really an LLM, that's not really like an LLM feature, but it's more to improve the customer experience. So having a separate validation endpoint is very, very useful for these features. Now, I'm low on time, but I want to talk a little bit on how we develop the platform to make these models convenient for practitioners to use. Because the reality is, especially in enterprise, a lot of the useful data for building these models is going to come from customers. And we, as well as many of you, will have promises with regards to your customers around safety using their data. The way that we manage this internally is basically by exposing a sandbox where users can use notebooks and use unapproved code only on open source data, data that's completely insensitive, and unrestricted data that's developed internally by Atlassian developers, not Atlassian customers. So again, this is another way for us to generate rich, useful content and data, which aligns to a similar distribution to what we expect customers will actually generate, but we know that it's safe. And it's the same sort of data where if we're training models that include data from Confluence, it's data that Atlassian developers have exposed to other Atlassian developers. That's the tier 1 of trust. The tier 2 basically means that everything to do with your code has to have been approved by our privacy team. It's approved that you're not mixing customer data because we don't do any sort of interleaving between customers. Every line of code is approved, every workflow is approved, even the parameters to your modules are approved. So your hyperparameters to your model are approved. So basically everything that has to do with customer data always has a level of approval. This might be annoying, except for the fact that practitioners have literally billions of rows of data that Atlassian has generated, so they often spend most of their time in that first stage before moving on, and that gives them a really rich ecosystem for developing. It also means that when they get to production, the code has to be very high quality, because it would be very annoying to review otherwise. So it improves the code quality. So, key insights. This page is a little bit old, but the short version is that model training takes ages and it's a pain, so make it as easy on yourself as possible. Make sure that your code for dataset generation is nicely modularized, that you can expand on it very quickly, that you can rerun it, and the same goes for your training code, and agree on that really quickly. Secondly, encourage your developers, if you're a platform team, to use version control through something like a trust system. This doesn't just work for trust and customer safety and data safety, but it also means that when your customers or your internal customers, developers, want to reproduce runs, you've probably stored something in your experiment tracker, MLflow weights and biases, that says, this is the version of the module we use, and here are the parameters. So reproducibility is easier. The third thing, come up with a framework, whether you use mine or not, for evaluation that makes it really easy to identify themes and weaknesses in your pipeline. And lastly, I can't iterate enough, the first dataset you make really will not be the last one. I think in the code generation use case, we were easily in the tens of dataset iterations. So yeah, follow a framework. And I think a good one, again, would be generate, paraphrase, complicate, then clean. Now for more concrete examples on actually fine-tuning models on Databricks infrastructure, I'm going to pass off to Brian.
Thanks, Nathan, for that insightful talk. So just as an intro, I'm Brian Law. I'm a specialist solution architect with Databricks in the Australia team, and I've been working closely with the Atlassian account on their journey through this as well. So let's look at what you need to do in order to do practical fine-tuning. So firstly, have a quick spot check. So as Nathan was saying then, have you actually gone through and tried to see how far you can take it with just a model? If there is no prompt that works, like even with like maybe low accuracy, then fine-tuning won't necessarily get there. In terms of going through and doing the fine-tuning process, then just like any other ML project, you're going through and you're optimizing to a certain target. So do you have inputs and outputs? Do you have samples that you can use to judge whether your fine-tuning is successful or not, and also as data to put in there as part of the fine-tuning process? And then finally, do you need really bespoke logic? If it's just that you're trying to answer questions in a new style, you're trying to go through and refine your application a little bit, you might not need fine-tuning. It might be a process of going through and experimenting more with prompts, experimenting with maybe breaking up your logic into different steps. You don't need to go through and do fine-tuning unless there's kind of like a bespoke logic you want to add as well. So there are various types of training. So we talked a little bit before about LoRa and QLoRa. So that's like the most VRAM efficient, but it's not as performant if you actually want to go through and bake in new knowledge. So particularly for domains like legal, like healthcare, where you've got specialized terminology and specialized concepts you're trying to break in, then LoRa and QLoRa might not get you there. You can go and do a full parameter fine tune. It gives you generally better performance, but then of course it requires more time and more GPU compute. And when you're doing that, you could find the model actually goes back in other areas as well. So it's important to have a good eval set, including things that might not fall within your use case, to see if the model's getting worse at other things. And finally, the most expensive is to do like a full continued pre-train. You need lots of GPU compute, you need lots of data. We're not gonna focus on that too much, but particularly, I guess, for new languages, then you probably need to go and explore that as well. So today we'll focus mainly on LoRa, QLoRa, and talk a little bit about full parameter fine tuning as well. So as we said before, this is kind of like the loop that you need to go through. You need to go through and create your data sets. You need to go through and train the model, do the evaluations. And it's not just about the evaluations. You need to have some sort of feedback mechanism to go and assess how useful this model actually is. So these are kind of the different parts that you need for each of these steps. Generating data, it's quite common these days to use prompt engineering and to make synthetic data sets. When you're going through and doing the model training, then that's the supervised process. For evaluations, then it's increasingly common to use techniques like LLM as a judge in order to go through and run through evaluation sets that might consist of thousands of samples. I will add, make sure you always do some manual validation as well. Don't just trust your judge prompt blindly. Go through and look at what it's actually saying. Once you've got that all sorted, your model's ready, then it's about going through serving up the model, and finally make sure you're always logging information from your customers and collecting sort of feedback for analysis as well. So we'll talk a little bit more about the data generation side and a little bit about evaluation as well. So firstly, what does it take to actually go and set up your data? The most common questions we kind of get is how much data do I need, what sort of format, and how to kind of go through and build it. And so let's look at the types of data you'll see there. So this is kind of like a raw text data set. You've just got things like books, like documents that you've ingested there. It's not something that you can take directly and then use that in a fine-tuning process. Generally, you'd go through and construct some sort of prompt response type data set, some sort of Q&A data set that you would then use for your fine-tuning process. You might also want to go through and construct a chat data set, particularly for long conversations, so that the model is able to follow the flow of a conversation and then eventually arrive at the answer that the end user needs. So the data, when you're going through and making these, it needs to be representative. So commonly, companies might have things like consumer Q&A pages. You might have call center logs in some businesses. Otherwise, you might need to look at handcrafted and synthetically generated ways. Now, of course, handcrafting is expensive and hard. So a common thing that you can do these days is to handcraft some samples and then use that as part of a prompt engineering workflow to generate the rest. And to generate it based on your raw data as well, so that it conceptually aligns with the terminology and the things that you're running within your business and in your product. So generating synthetic data sets, then LLMs are quite good at these. In terms of going through and actually generating full conversations and things like that, then you need to go through and assess carefully that the generations actually line up with what you want. So there are packages out there like Ragas, like Llama Index, for example, that have Q&A generation as part of there, but make sure to review those, and it might not necessarily line up with what exactly you want. So the process to go through, you need to think about a lot of different things. And it's not just about the exact Q&A, but the model will get affected by things like the tone, the syntax, the thoroughness of answers, and also even things like the answer length as well. So it's going to be a cycle that you go through. Raw text, Q&A, refine and refilter that data set, go through and train, evaluation, and repeat. It's not going to be a one-cycle process. You need to go through and do this multiple times. So it's sort of like how much data is enough. And then there's, I guess, no concrete answer to these. So you can start with a few hundred. You might even be able to get results just on like 10, 20. But the more generally, the better. But you've got to make sure it's representative as well. So during the training loop, this is what we'll be running through. We need to get that import data set. We need to get it formatted and pre-processed. And there's some of the technologies that you might see in that space. Then we need to go through and set up the main training function. So this is the main loop that we're going to use to iterate through our data set to calculate our losses and to do things like distribution as well. And then finally, we need to go through and look at things in terms of the logging and the monitoring side of things as well. Because if you don't have logs, if you're not monitoring the training process, then it might not be doing exactly what you want. Your loss might not be dropping. You might have issues with hardware faults and other things as well. So in terms of training techniques, probably the key thing is to understand VRAM. So these are some experiments that were run by people in a research lab. And they were using 2x 24 gigabyte VRAM. I'm guessing like probably most people in this room will be able to get access to cards like the A10Gs or like a 4090 or something like that. So it gives you an idea of what you can kind of achieve even on like small GPU poor type setups. In this case, these benchmarks there are based on the Llama 2 7 billion model. So you can see when we go from just a standard LoRa adapter to a QLoRa, then we can save a lot of VRAM, and then that gives us the ability to train faster. Of course, quality will also be affected by the quantization process, so it's something you'll need to experiment a bit with. When you're going through, then you also need to consider things like context length as well. So context length is kind of the number of tokens that we're going to put through there. So the longer the context length and all of that, that's going to have an effect. And another thing that we can do is to look at things like CPU offload. So here we've got a chart here that's looking at CPU offload. CPU offload is where during the training process, we copy some of the data that we don't need right now back onto your CPU as well, onto your standard RAM. Now, the problem with that is that's going to affect the performance. That means you've got more I/O going on. But if you don't have access to a lot of GPUs with high VRAM, it's something that you need to go through and look at as well. So in terms of navigating this, first thing, make sure the model fits. Use LoRa, and you can test QLoRa as well, but use the evals to decide which way you want to go. And you'll go through and increment the batch size until you kind of max out on RAM. Now, it's not important to go through and try and optimize and get 100% GPU utilization with only, like, say, 1 megabyte of free VRAM left, because there might be occasional spikes in the VRAM usage. So if you're incrementing batch size to the limits, then you might get crashes partway through. So you want to make good use of your VRAM resources, but always leave a bit of a buffer when you're going through and setting it up as well. Now, there are sort of like complex processes to go through and calculate, but you can go through and look at some of the numbers I put earlier to sort of get an understanding. Now, let's look at kind of the data generation process. So firstly, you're going to start with raw data. And then raw data, the thing is that language is complex and sentences has different lengths. So this is not good for going through and doing matrix multiplications. So you've gone through, you've generated your Q&A data set. You're going to have a variety of different samples, different lengths. So what the data pre-processing step is going to do is to firstly, we're going to go through and we're going to encode that into tokens. So this is the tokenization of those sentences that we had there before. So that's the first step in the data loading side. And then after that, we're going to go through and we're going to pad out the lengths because that's what we need as part of the fine-tuning process. And this is why it's also important to look at things like the length of replies when you're going through and constructing your Q&A. Once we've got sort of that, the numbers in there, once we've got it padded, once we've got it encoded, then the data loading step is going to go through and shard that across to multiple GPUs as well. So you need to consider all of these things when you're going through and doing the setup, looking at lengths, looking at context, and then looking at how that data set will shard across as well in order to make sure that you're getting an efficient fine-tune. So we've looked a little bit at data loading, we've looked a little bit at data generation. Let's talk a little bit about the main training loop. So what happens in the main training loop? Firstly, we load the weights from the file. Then we need to go through and adjust the layers for quantization, for LoRa adapters. And then finally, the model needs to get moved and sharded to GPUs, or sharded if you've got multiple. And that's part of the process. The next part of the training loop is to go through and set up things like the optimizer, things like the learning rate schedule, things like sharding configs or zero optimization if you're using deep speed, and even things like looking at the loss calculations as well. So I guess to what Nathan was saying, going through and trying to home spin all of this can be very complicated and error prone as well. There are countless times I've seen where maybe there might be a minor error in the loss calculations, and then that's going to totally throw your fine-tune off as well. Now, as you go through and actually train, then the training process is going to be unstable as well, potentially. So you need to make sure that you've got proper logging and monitoring set up. Common things that we see is sort of spikes in losses from maybe changes in the distribution of the data that you're putting in there. Maybe it could be something you coded wrong as part of the training loop. Checkpointing is very important as well and can also cause issues because when we checkpoint, we need to go through and save the weights out. If we save the weights out sort of synchronously, then we could block the training process as part of that. Once you start to move and scale up your job, once you start to use more GPUs, you're going to have to think about things like hardware failure as well. And then finally, as I said before, it's quite common for maybe there to be some mistake in the loss calculations. So we've gone through, we've talked about data pre-processing, we've talked about the data loading step, we've talked about kind of the main training loop as well. How can you kind of like go through and scale this up? Generally, I'd say always start with a single GPU, make sure your loop is going through and working first. Make sure things like the loss is working out, make sure your checkpointing and logging is running properly. Then you can sort of like go through and add GPUs on the single node. Firstly, you'd probably go with 2 GPUs. That's enough for you to start debugging faults. You can go through and make sure that the training is being distributed. You can go through and make sure that the loss is still decreasing. You can go and make sure that logging and checkpointing is still working even after distribution. It's quite common for these things to start breaking when you move to a distributed setup. Then finally, you want to try and max out on one node. It's always easier to go through and use 8 GPUs on a single machine as opposed to trying to get 8 machines with 1 GPU each. So in terms of Databricks, then you can start with like a Databricks single node cluster. The ML runtime that we've got has most of the libraries that you need pre-baked in there. And then you can use the %sh and the ! Python magics in order to directly execute code on the node. And if you need sort of like specialized OS dependencies, you can go through and use an init script to set that up. I've got a repo that I've linked here that you can look afterwards that contains some of the notebooks that you'll need and some of the examples of how you can go through and execute that. So that's a screen grab of going through and training on a single node with a Python script. Once you start to scale it out, then you'll need to look at something like the torch distributor or the deep speed distributor. Again, on that same repo, I've got a sample of how you can go through and scale out a training process. When we look at distributed, there are a lot of things that sort of start to kick in that make it hard. So you've got different nodes. Different nodes have the different GPUs on there. Each of the GPUs will need to have a collection of the weights, a collection of the data. There's synchronization that happens, and all of that network overhead will make things slower. Hence why you want to try and scale up on a single node first, and then maybe move on to multi-node later on. So these are probably some of the key things that you need to look at. In terms of going through and doing things like hyperparameter sweeps, learning rate's probably the primary thing you'll be looking at. Otherwise, it's iterating on that data process, generating more samples, generating more valuations. Everything else is mainly just about making it fit on your hardware setup and making it kind of efficient. So there are things like zero stage with deep speed. You've got CPU offload, like I mentioned before. You can go around and mess with batch size and gradient accumulation in order to try and make good use of your VRAM. And then quantization as well to shrink models down. So for learning rate, then these can be case specific. So I remember talking to Nathan early on in his journey, and then he found like just a magic learning rate that seemed to make things work better. When we go through and we're starting to look at things, making things fit, then 16-bit is usually a given these days. 8 and 4 you can experiment a bit with, it definitely affects quality. In terms of like sharding and zero, then you want to be using full shard. You want to go through and do sort of zero optimization. Offload can be hardware dependent, you need sort of fast SSDs attached. And then batch size, as I said, go through and adjust that and make it fit on your VRAM. Now, evals. As we said, key is evals. So you need to have representative questions. You need to be able to have full coverage of the types of questions and answers that your users are going to be putting in there in order to run evals. And make sure to test general knowledge as well. Maybe like it starts making grammatical mistakes once you start fine-tuning on too much data or if your input data is bad as well. So it's not just about testing your specific use case. Make sure you're testing a bit more generally as well. And make sure to try a lot of different topics and different question types to make sure that the evals are kind of representative of what you might get. As I said, it's typically common to use LLM as a judge, because that's the only way you can really scale. It's not efficient to try and get 100 people to manually write Q&A. So when you're going through and using LLMs to do evaluations, then firstly, remember that LLM judges are not the same as a customer. So it could be doing things wrong. You need to go through and calibrate the process, and you need to spot check and review what these judges are doing as well. So definitely do not skip the manual step on this or you'll suffer. So a quick review. We talked through about prompt engineering, we talked through about sort of the fine-tuning process and a little bit about the eval process. Once you've actually got your model deployed, make sure you're collecting feedback, make sure you're keeping monitoring it in production, and adjusting your eval set as needed if it turns out that the way your customers use your model are different from what you expected. So I guess like one last thing, it's like very complicated, there's lots of code, and part of the Databricks vision is to try and make things easier. So something that we've got coming soon is the Databricks fine-tuning product, and you'll hear a lot more about that over the next couple of days as well. And where that fits in there is specifically on the model training side of things. So what is the Databricks fine-tuning in 1 minute? Firstly, it's like a full SaaS solution. So we're running all the hardware, we're managing the GPUs, we're managing the hardware faults. So you don't need to worry about the GPU side of things. Scaling is baked in there, so you don't need to worry about all the sharding and scaling setups. And there's not a lot of boilerplate in terms of going through and setting up the training loop. So then you're just doing a simple API call, you point it to your data set and to your evaluations, and you can see the API call that you need in that screenshot there. So if that's something you want to try out, then it's something that we've got in our demo library now that you can look at. And that will give you more time to go through and look at how you can build your evaluation data sets, how you can do your data set generation for the fine-tuning side of things, and not have to worry as much about doing things like sharding, doing things like writing distributed code, and doing things like managing and monitoring the process and the hardware as well. So hopefully you learned a bit there. We had Nathan to go through and talk about his experiences at Atlassian on going through and building a code generation model. And then we've gone through the exact mechanics step by step of going through, loading your data, training your model, and doing evaluations. Thanks for your time today, and hope everyone learned something.
Thank you.